Hi, and welcome to my podcast. Today we're going to talk about the recently given Nobel Prize in Physics, awarded to three brilliant scientists by the name of Sean Perlmutter, Brian P. Smith, and Adam G. Rice, for their work in astrophysics. To be more specific, we're going to talk about their work using Type 1a supernovas to determine the expansion of the universe. Ever since humans have wandered the Earth, there's always been a certain fascination of the sky. All the stars out there in the great unknown have often left people behind with a profound wondering. What is out there, and how far does it stretch, are two of the most common asked questions that we still ask today. But recently we gained a better understanding of what is out there and how far it actually stretches. In this podcast I'll try to answer these questions and show how they're actually two parts of the same answer. Today it's widely accepted that the universe consists of ordinary matter, which makes up 4% of the universe, dark matter, which makes up 26% of the universe, and the more elusive dark energy, which makes up a stunning 70% of the universe. With a staggering 70%, dark energy makes up the vast majority of the universe, so this is what we're going to be focusing on today. But also, dark energy is an effort to describe how big the universe is, or more specifically, the expansion of the universe. So let us start with how scientists discovered this expansion. We all heard of the Doppler effect. Maybe not by name, but we all heard the effect of it. When an ambulance presses towards you, the sound originating from it has a much higher frequency than when it's moving away from you. This is due to the Doppler effect. The sound waves are first compressed and later stretched, which gives the effect of a higher frequency and a lower frequency. All of this is of course compared to the frequency of a still standing ambulance. The Doppler effect is also true for light, but instead we see oncoming light distinctively more blue and outgoing light distinctively more red. This is called redshifting. By using this method, a physicist by the name of Edwin Hubble discovered that galaxies are moving away from us in all directions, and therefore concluded that the universe must be expanding. Even though he could tell that the universe was expanding, he could say nothing about the rate of the expansion. This was due to the fact that galaxies which are close to us with low intensity look very similar to galaxies far away from us but with high intensity. This made it very hard to tell how far away from us the galaxies were. To get any information about distance, we need to know something about the intensity of the light reaching us. This has been a problem for astronomers for many centuries. The solution, however, showed itself in the form of a Type 1a supernova. A Type 1a supernova doesn't have any problems with the low intensity of light. In fact, just one of these Type 1a supernovas can in a few weeks emit as much light as an entire galaxy. This type of supernova explosions happens when a white dwarf star, which is a star as dense as the Sun but as compact as the Earth, in a binary star system, enters the last stage in its life. So if the white dwarf is part of a binary star system, which is often the case, the white dwarf gravity steals mass from the other star. When the white dwarf's mass exceeds 1.4 solar masses, it can no longer keep together. When this happens, the inner core of the white dwarf becomes so hot that the fusion process runs wild, and the white dwarf goes supernova. The fusion product emits a powerful radiation, which intensifies in the weeks after, and then slowly decreases. The advantage in using a process like this is that one knows exactly how much energy is released, and therefore how big the light intensity is from a Type 1a supernova. This means that one can look at a Type 1a supernova which happened many billion years ago and a Type 1a supernova which happened quite recently and compare them. In other words, scientists now have a standard candle to measure distances in comparing how much light that hits us. Via all of this knowledge, scientists could now make predictions regarding the expansion of the universe. If the cosmos expansion had lost some of its momentum, the light from a Type 1a supernova would look brighter. But instead scientists found that the light got dimmer and dimmer. The widely accepted theory was that the universe was expanding, but due to gravitational forces of the mass of the universe, the expansion was decreasing. So this method was first meant to tell scientists how far the universe was going to expand before reaching its turning point. But what scientists found was far from this theory. Instead of the universe slowing down, they found that the universe was in fact speeding up. This had to be some kind of reverse gravity, not attracting but repelling galaxies en masse away from one another. This reverse gravity was called dark energy. dark, not because of its color, but referring to our ignorance regarding its nature. So this is the true answer to a question about what is out there and how far it stretches. It now seems that the universe is filled not with stars, but with dark energy, and that this same dark energy also is the force determining the size of the universe. But also another interesting discovery was made in this research. Dark energy hasn't always dominated our universe. The three scientists' research showed that in the first 7 billion years of the universe, it was dark matter which was the dominator. This helped galaxies form and allowed ordinary matter to lump together. As we now know, the next 7 billion years, dark energy became the dominator. Scientists are now in the middle of clarifying exactly when this change happened. This will help us to understand what dark energy is, and this will lead us to a better understanding of who will become the winner and who will become the loser in the big cosmic battle between dark matter and dark energy. Will the tide shift again, or will the universe just keep on expanding until it rips everything apart? These are just some of the questions modern physics is trying to answer.